All right, so welcome back. Week 5 already. Wow, we're in week 5 of Physics 325, and we're entering into part 2 of the course. We skipped week 4 because of the test, and now we're into some new material. Part 1 of the course was all about the fundamentals, reflection, refraction and interface, the properties of the electromagnetic waves, and how we can think of them as photons and rays. And part 2 of the course is about phenomenology, diffraction, polarization, and dispersion. So really what we're going to be doing now is we're going to be taking some of the stuff we learned and generalizing it. Now, in the first part of the course, we often relied on the fact that we can justify doing this just with plane waves because we can build up complex waves, more complicated waves, from individual plane waves. Okay, and we're going to start using that now. And the language that we're going to use for that is called Fourier Analysis, which is the topic of this video. Okay, so let's start with our goal, which is going beyond single plane waves to make more realistic waves. All right, this is what a single plane wave looks like. It's beautiful, it's simple, we can do all the math on it. And if that was it, we had to do new math for new types of waves. It really wouldn't have been worth all the effort because all we concentrated on so far were the plane waves. But it turns out that although plane waves aren't even really realistic, they go infinitely far in space and they transport infinite energy, we can represent realistic waves as superpositions or sums of plane waves. And the heart of this trick is the superposition principle. Okay, and that basically says that if we have one plane wave and we calculate how a system responds to it, and then another plane wave and calculate what the system does to that, I can form a new plane wave or new wave rather, not a plane wave, by summing up the two individual plane waves. It's going to make something that does not necessarily look like a single sine wave. And do I need to calculate any new things, any crazy new properties of the response? No, I just add up the original answers that I got. And this is the heart of the superposition principle. And this is where we're going now. We're going to make kind of any complicated waves that don't necessarily look like this. They might look like this, or a little pulse of light that's going along. And either of these things can be represented as individual sine waves, it turns out. So we need a language that's going to help us work for that. And fortunately, such a language exists, and it is known as Fourier Analysis. Okay? Fourier theory. So what Fourier theory tells us how to do is how to work with multiple sinusoidal or multiple harmonic functions, whether it's a sinusoid or a complex exponential. Okay? And the reason is that we can take this. We can take this plain, beautiful plane wave, and we can do a very simple factorization. We can factor it into a spatial part times a temporal part. So when we can ask ourselves, when we're adding up many plane waves, what does that mean? Are we adding up many different frequencies, many different k vectors, or both? And we're going to concentrate on each one of them individually. This lecture is going to be about looking at different times, and the next one is going to be looking at the spatial degrees of freedom. Okay, so this time degree of freedom here says that if we have multiple frequencies and we add them all up, we're going to get a complicated signal in time, right? And it's going to look something like this. We're adding up a bunch of things which are none other than plane waves, and the sum of all these things looks very much not like a sinusoidal wave, all right? On the other hand, we have this other degree of freedom. We can add up many k vectors, and what does that mean? Well, it means I'm mostly propagating along a given angle, say z, but then I'm adding a plane wave going at this angle, plus that angle, plus that angle. Remember, the k vector tells us which direction the wave is going. So as I'm adding multiples of those up, I'm going to get complicated spatial patterns that are going to form because of interference. Okay? And that's going to look something like this. So adding different k vectors in this way will be the spatial degree of freedom, and that's going to be next week. We're going to talk about that next week. That's diffraction. Okay, so this week, we're going to talk about the temporal domain, the time domain. So let's start with that. Really what we're going to start with is two pictures for looking at phenomena. We can talk about a signal which varies over time, or we can talk about the frequencies that compose that signal. Take a single sine wave. We can represent that as point at time 1, time 2, time 3, and we can describe all the times this way. It's a sinusoidal function. But really, if it's a sinusoid, it just repeats forever, and all we need to tell ourselves really is the frequency. If I know the frequency of this thing, I can just write that number down. So really I could have just replaced that with a single point. a frequency. So I can plot on the x-axis frequency now, and just how high up is how high that amplitude is. And this is what we call the frequency domain versus the time domain. So I can represent multiple sine waves and cosine waves this way. All right, so let's do that. We're going to add, you can see here, sine waves of different frequency, and they'll appear as different points in frequency space. And interestingly, if I have multiple sine waves, I can clearly see that in frequency space that it's just 2 or 3 frequencies here, but in the time domain, it looks very complicated. It does not look like a sine wave at all. It looks kind of like a triangle wave, all right? And the key to this Fourier analysis is that these two pictures are completely equivalent. If I know one, I know the other one. And this is very powerful, very great, because sometimes it's much easier to work in terms of frequencies than in terms of time. So the language we're going to use to attack this problem is Fourier analysis, and it's going to tell us how to relate the frequency domain to the time domain. I have to give one snippet, a caveat, to keep ourselves honest here. I've written this as one vector in one direction. It turns out that's not enough. We need 2. Why do we need 2? Because we have to specify not only the amplitude and the frequency of it, but its starting point, its overall phase. So let's see what I mean by that. So if I have, for example, sine some amplitude of omega t plus some arbitrary starting point, some arbitrary phase, that's all that phase is, right? I can do a trig identity and factor out a cosine phi times sine omega t. And the other part of that trig identity, which is sine of phi times cosine omega t, is just that sine a plus b identity. So I can represent that as an amplitude of the sine part. So we'll just call this we'll call it S maybe, and C times cosine. So I can represent the sinusoidal function with any phase as 2 numbers, as a sine part and a cosine part, or say an axis this way and this way to really keep myself honest. And similarly, I can do the same with the complex exponentials, because I can write e to the I omega t plus phi is e to the I phi, cosine omega t plus I times sine omega t. And this is just going to be, from Euler's formula, some a plus ib. So I can multiply that all out, and I'll have a real part and an imaginary part. Again, we need 2 numbers to represent the phase as well. Okay, so with that off our chests, we're going to continue. It often is sufficient just to talk about the magnitude of it. So we can get away with just looking at one-dimensional frequency space here. I had to say that for legal reasons, but let's continue with analyzing this. So Fourier analysis, what does it actually say? It says if we have a function which is periodic with some frequency t, which we can write as some period t, which we can write as some fundamental frequency, just 2 pi over t, I can represent any complicated function in terms of sines and cosines, right? This thing, even though it does not look like sines and cosines, is equivalent to a series that looks like that, okay? So it's a sine plus b cos with some coefficients. Similarly, I can do the same for a complex exponential, okay? And you say, well, that's great, good for you, but what are these a's and b's? If I don't know the a's and b's, it's still, I can't actually plot this thing. I can't actually work with it. Luckily, it turns out that we can directly calculate these coefficients. And we won't calculate these coefficients in this class. We'll leave that for your math professors. But the basic idea is that we can calculate them with these formulas. And if you want to derive these, it's actually not too bad. Use the fact that sine is an odd function, cosine is an even function, and as a result, these things are orthogonal, the sines and cosines that have a multiple of a given frequency. So I basically just integrate this definition here, and I can extract the coefficients a and b in. Exercise to the interested student, or we can talk about it in office hours if you want. But these are the coefficients that you get, with the edge case that the first zeroth order, zero frequency term is just the average of the function. And similarly, we can do that with the cosine, with the complex exponential part. All right. So let's actually look at an example of this. Now, I don't want to go too far into the Fourier theory, but just so you don't think I'm full of beans, let's calculate a very simple case of a periodic square wave that has some amplitude a, some width a, which we'll call t over 2. We'll just keep it simple. And the period here is t, right? So we're at minus t over 2 to t over 2. And half of that, it's on. The other half, it's off. This is a nice symmetric square wave, which does not look much, to me at least, like a sum of sines and cosines. It has these sharp edges, square, not this curve. So let's actually calculate the coefficients and see what sines and cosines make this up. We can work either with the cosine sine representation of the complex exponential. Let's go with the complex exponential and see how we'd actually calculate this. So Cn is equal to 1 over the period, integrating over one whole period of whatever that function is, this is general, times e to the I n omega, and for clarity we'll call it omega naught. It's the fundamental frequency, 2 pi over the period, times t. Sometimes I get lazy with my omega naughts, sorry about that. Our function here, what is our function? Well, our function is equal to a constant a if we're between negative t over 4 and t over 4. So we'll just say absolute value of t is less than t over 4, right? That's going to be this point and this point, half of a half, and it's 0 otherwise. So for example, if we're between negative t and a half and a quarter of t, or t over a quarter and t over a half. Okay, this is our function. Just have to write it down somewhere. Sometimes that's the trickiest part to actually do these problems, is actually writing down what the function is. So we're going to plug that in for this thing. And basically it's going to be a constant either way, which is either 0 or a. So it's 0 outside of the absolute value being a quarter in these regions here. So we don't need, the integral will go to 0, and all we need to include is the part outside that. So minus, or rather inside that, t over 4 to t over 4. And then what do we get here? We get this integral of this part, n omega naught times t dt. Okay? So this is an easy enough thing to integrate, right? So it's going to give us, if we integrate it, a 1 over n omega naught here, a over t times I n omega naught, and the value of this integral is this evaluated its endpoints, so it's e to the I n omega naught times t over 4 minus e to the minus I n omega naught times t over 4. Okay, and let's do a little bit of simplification. So first of all, we're going to note that anytime we have omega naught t, well, that's equal to 2 pi over t times t, which is just 2 pi, right? So omega naught t, which appears a few times, is going to give us a 2 pi. And we're also going to use a trick that sine of x is equal to e to the ix minus e to the minus ix over 2I. Just plug that into Euler's formula and you'll verify it. So that's going to give us, we're going to have a 2 pi I here, so I'm going to go over n pi, and I'll bring the 2I in just to be tricky, e to the I n pi over 2, it looks like, if I'm doing my math right, minus I n pi over 2, is that right? Yeah, 2 pi over 4, pi over 2, over 2I, which is just our sine of n pi over 2. Very nice. So that's my coefficient. So my Cn is equal to, what is my Cn equal to? It's equal to a over n pi times this sine of n pi over 2. Okay? So if n is equal to 1, let's look at a few cases here. So n is equal to 1. We'll start at 1 because it's a bit problematic for n equals 0, but we can just use the fact that we said earlier that at 0 it's going to be the average of the function. So we'll start at 1. Sine of pi over 2 is just 1. So that's going to be a times pi. At n is equal to 0, or sorry, n is equal to 2. I just said I didn't want to do n equals 0. We have sine of pi. Sine of pi is 0. N is equal to 3. I'm going to have sine of 3 pi over 2. That is negative 1. That's going to be minus I over 3 pi. N is equal to 4, 0. N is equal to 5. Negative 5 pi over 2 goes around once and up. That's 1. So it's going to be a over 5 pi. And we can see the pattern. So it's going to be equal to a over n pi times this weird minus 1, and we can kind of extract that by saying n minus 1 over 2 if n is odd, and 0 if n is even. Okay, so these are my CNs here. So these are the frequencies I need to add. Okay, and we can plot them. It really helps to visualize this. So we've done our math. Let's actually do get the benefit of actually seeing what that looks like. And we're going to build our square wave out of individual sines. So the first thing we've got to add to our first or 0th approximation really is to add the C0 term, which is just the mean. There we are. There's our approximation to a square wave. Not great, but better than nothing probably. Let's add a couple more terms. So we'll add n equals 1 and n equals 3 term here, and just plot them as I have. As I increase them, we can see what happens to the wave there. It's already looking kind of squarish, which is interesting. We have 2 sinusoidal functions already, plus a constant, and it already is approximating the square wave starting at 0 and going to 1 here. That's neat. Let's see what happens if we add a couple more terms here. Okay, so we'll add one after the other. And you can see that. Let's do that one more time. That's kind of neat. Look at that square wave as we're adding these terms here. It's very, just with a few terms, it's really starting to look like a square wave. And furthermore, we can kind of see a pattern emerging in frequency space here. So if we tilt our heads just right, we can see a pattern that looks something like that. All right? And it has to do with this negative 1 to the n minus 1 over 2. It goes up and down and up and down. And this 1 over n term here means that it's getting smaller. Okay, and that's quite neat. That's our approximation to a square wave. We can add a ton more terms if we want and get a better and better approximation. So a square wave is really a sum of sines and cosines. But I think this leads to something even more interesting. Now, if we really pay attention to what's going on in frequency space here, the frequencies are evenly distributed. They're distributed by 1 over the period, right? It's proportional to 1 over the period. So if this period was longer, was wider, the frequencies would be closer together, and vice versa. But let's think about this even more fundamentally. What does this mean if we don't have a symmetric square wave? What happens if we have a more sparse train of pulses, right? The period compared to this width here is going to get bigger and bigger and bigger. Now, according to this argument, we should have the same kind of overall shape, but the frequencies are going to get closer and closer together because the frequencies are somehow proportional to 1 over that period. And this is going to be something we're going to see time and time again, especially in this week. Okay, so let's try to animate that. Let's zoom out. Okay, we're going to zoom out and we're going to try to separate these square waves, and I'm just going to calculate the Fourier transform along the way. Okay, so let's separate the pulses and see what happens. Pay attention to what's happening in frequency space here as we do this. You see that? We get the same pattern, the same overall pattern, except the frequencies are closer together. Let's do that one more time. Okay, so we separate them. We get longer periods, shorter frequencies, but the same overall pattern emerges. Okay? What happens if we take this to its logical conclusion? What happens if the pulses get infinitely far apart? In other words, we have an infinitely long period, or we have an isolated pulse. I'm allowed to do that. I have a laser pointer here. I can go like this. There, I've just created a pulse. And well, it did repeat itself there, but I could, in principle, just do it once and then never again. What would that wave look like, right? What would that pulse actually look like? Well, we can do that according to Fourier theory. We just have to apply a little bit of a hack. The hack is that Fourier theory tells us anything that's periodic with period t can be represented as a sum of sines and cosines with a spacing proportional to 1 over t. Okay, so it's periodic. The period just happens to be infinity. It's the age of the universe or something like that. In other words, we have an isolated pulse here. According to that, we can still represent it with Fourier theory in that limit. It's just that in that limit, the frequencies are going to become infinitely close together. What does that even mean? Well, let's try to have a look at that. So let's continue that spreading out of the frequencies. And look what happens in frequency space there. It becomes a continuum. All right, we have an isolated pulse, and in frequency space, it's no longer a bunch of isolated points. It's just a continuous distribution of sines and cosines. All right, and really we can see that from our definition of Cn e to the I omega n t. We're going to take the limit as this change in frequencies, or rather the limit as t goes to 0, infinity, sorry, 2 zeros, the limit as t goes to infinity, and the frequencies therefore separate. This omega naught of this, and it's going to become an integral, right? So here we have our definition here. Our sum will become an integral. Instead of a discrete sum, we get a continuous integral, which is kind of what an integral is, right? So we can really think about extending this idea of Fourier series to continuous distributions of frequency, right? And in that case, the sum becomes an integral, and it's no longer called a Fourier series, it's called a Fourier transform. So it's this integral transform that is actually a map. It's a map from frequency space to time space. And we can do an inverse Fourier transform, which is just doing the other thing. It's the same form. It's just we flip the sign in the exponential, and it's going to take us from time to frequency. So we got frequency to time, time to frequency, and we can just do this continuously. Because if I take the inverse Fourier transform, the Fourier transform, I get the function back. It is the inverse, right? So I can take the Fourier transform of something, take this inverse Fourier transform, which is pretty much the same as taking the Fourier transform, just a different sign in the exponential, and get the original function back. Okay? Very neat stuff, very deep stuff. We're going to use it quite a lot. Now, just so you believe me, I want to do another very quick calculation. Let's actually calculate the Fourier transform of that isolated pulse. All right, so let's take the Fourier transform of f of t is equal to a when t is less than, absolute value is less than a over 2. We're just going to call it a over 2, where the period was 2a here, and 0 for all points of time after that. So this is the same as the last time. Just plug in a is equal to t over 2. So let's look at our Fourier transform here. I'm just going to plug in the definition. So we're going to get f of omega is equal to 1 over 2 pi. It's just some normalization constant. Integrate over all possible times f of t, whatever it is, this is general now, minus I omega t dt. Okay? So, what is our t here? Well, it's 0 most places. It's the only time it's not 0 is when it's between negative a over 2 and a over 2, in which case it's a. So we can write that as a over the integral of, so a over root 2 pi times this integral between a and over 2 and little a over 2 of this exponential dt. Again, a fairly easy thing to compute. So it's going to be what? It's going to be a over root 2 pi times negative I omega times e to the minus I omega a over 2 minus e to the plus now I omega a over 2. And we'll do the same thing. I'm going to multiply this by 2 over 2, and we'll get that minus I in there. And this, top and bottom, if we just multiply by a minus sign, this will become a plus, plus and minus. Here's our nice sine function again, right? Sine omega a over 2. Okay, so let's see what we have here. We can rewrite this as a over root 2 pi times sine of a omega over 2. But we also have this omega here. So we can actually pull that in. I can pull that 1/2, that 2 here, and I almost have the same thing. So I'm just going to do this. I'm going to multiply a over a, and I have this sinc function, sine x over x, right? Sometimes known as sinc x. And that's a sine x over an x. Remember, in the limit, sine x equals x, so it's well defined at x equals 0. So I get a times 2 pi sinc of a omega over 2. And here's 1 over x, and here's I sine. That's the Fourier transform, the frequency distribution of my square. So if I just take a pulse, take a very short pulse, blip, even if that pulse is monochromatic, a single frequency, by blipping it on and off, it's equivalent to a continuous distribution according to this sinc function of a bunch of different frequencies. And that's exactly what we see here. In the case that we had a periodic square wave, we had that exact same envelope, this sinc function. It was just discrete frequencies filling that envelope. So I just want to talk about one more thing in this lecture, extension to multiple dimensions. Okay? Now we live in 3-dimensional space and 1-dimensional time, so we have 4 dimensions of space-time. We had period t, which is 1 over this 2 pi over the frequency, or rather the frequency is 2 pi over t, same thing, in time, and we have this Fourier transform relating frequency and time. For a spatial frequency, we have a spatial period, which is the wavelength, how long in space the wavelength takes to repeat, and we have an equivalent to omega, which is k. We haven't thought of k this way before. K is the spatial frequency, the spatial angular frequency. It's the analogy to omega with time. Okay, so it's 2 pi over lambda. And we can just change symbols. Instead of a omega, I'm going to write a k. Instead of a t, I'm going to write, say, an x. And it's the exact same math. I just interpret it differently. So if we have a pattern in time that's doing something, I represent that as a sum of omegas. I can just have that same pattern in space, and it's going to be a sum of k's. Now in space, say if I'm even shining onto this sheet here, I have 2 spatial dimensions. I have x and I have y. So we're just going to do the same thing. We're going to take the Fourier transform along x, the Fourier transform along y, just brute force plug it in. This is it. Literally, this is just 2 Fourier transforms that are multiplied together. Okay, 1 along x, 1 along y. And I can relate the spatial frequencies, right? And this is really just in Python adding up these different signs in x and y space, which correspond to my different k's. And this is the pattern I get. I can do this with any shape. For example, an important one is the circle. So I take the Fourier transform of a circle, and I get this oscillating, what's called a jinc function, actually. It looks almost like a sinc function, but it's a Bessel function, it turns out, which is very, very sinky. It's just a slightly different functional form, and it's like a Bessel function of x over x. They call it a jinc. We'll get into that much later in the course, but this is just an important thing to note that we can do it. We can look at the Fourier transform of a circle, and this has huge applications in imaging, how well you can image something. Because we'll see if we try to image something through a circular aperture, meaning either our eyes or a big telescope, and we're looking at something coming from far away so that it illuminates that entire circle, a point will not get mapped to an individual point, it'll get mapped to a jinc. So this is very important later in the course. We don't need to know too much about it just yet. Let's summarize. This is a lot of material today, as usual, it turns out. Let's summarize what we learned. Okay? So the first part of the course was about single frequencies, single plane waves. Now we're going to add up multiple plane waves, and the language to add up multiple plane waves is Fourier analysis. For things that are periodic, we can represent signals, for example, in time as discrete sums of sines and cosines or complex exponentials. If we take the period to be infinitely long, we just have an isolated function. Doesn't even have to be periodic now. We have a continuous distribution of sines and cosines. And that is given by the Fourier transform. The Fourier transform is just a mathematical integration we can perform. And when we do so, we get a mapping from time domain to the frequency domain. Okay, so next time we're going to start using this when we look at dispersion, which is the index of refraction looking different for different frequencies. And we will see you then.